Hello, can you hear me? Hopefully you can hear. I'll be doing my second video on ionizing radiation and nuclear reactions. Two. I'll be doing the second two topics of the big topic. So the first question will be on, let me find it, radiation and the environment. So radiation and the environment. Okay. First question. It says that as a result of a nuclear as a result of a nuclear bomb testing, strontium-90 has entered the environment, and strontium is chemically similar to calcium, and if ingested may end up as a long-term component of bone. A resident of an affected area is found to have absorbed strontium-90 with an activity of 100 megabecquerels. Wait, becquerels. Becquerels. Yeah, okay. The half-life of strontium-90 is almost 30 years, so the decline activity may be ignored if the radiation dose is relatively large. And part A of the question asks us the energy released in each decay is 2 times 10 to the negative 13 joules. How many joules of energy we released from his bones each second? So first we know the activity, which is 100 becquerels. Becquerels. Yeah, becquerels. 100 megabecquerels. And then we can use the activity formula, which is like A equals N over T, where N is the becquerels, and then T is time, and wait, no. N is the number of, is the number of this integration, right? So then we can find out what that is, and then we can use it to find energy, as it's basically the same as decay. So it says in each second, so we'll assume that time is 1 second and activity is, should write here 100 megabecquerels. Okay, so that's just 100 times 10 to the power 6 becquerels. So that's 100 times 10 to the power 6 equals N of, I don't want that. Can I remove? Okay, that is N over T, which T is 1, so that means N equals 100 times 10 to the power 6 joules per second. Yeah. Wait, no. Oh no, the energy released in each decay is 2. I'm gonna find out. We want to find out, because this is the number of decays that will happen. It says in each decay is that much energy. So okay, so that's decays, let's say. And then that means the energy released in each second would be 100 times 10 to the power 6 times 2 times 10 to the power of negative 13, which we use a calculator, and then we use 100 times 10 to the power 6 times 2 times 10 to the power negative 13 and we get this really small number, which is just 2.00 times 10 to the negative 5 joules. Is it an estimate? Energy released in each decade. I think it's an estimate because I don't know. Nuclear energy is never certain. I think. Oh well, whatever. It should be fine. To get like 1 mark deducted, it's like decent. Okay. Part B. Um, is the patient has a mass of 60 kilograms. Calculate his daily, that is each 24 hours, absorbed dose in grays. So now we can use the Gray's formula thing. So that's AD equals E over M. So that's just energy over mass. So it's 2 times 10 to the power negative 5 over 60. But that's each second. We want the daily intake. So we times 60, make it minutes. Times 60, make it hour. Times 24 equals day. So that is that divided by 60 times 60 times 60 times 24, and that is 2.88 times 10 to the power of 1 2 negative 2. Oh, that will be grays that the guy will intake each day. Yeah. And for part C, whoa, okay, part C asks the radiation is a mixture of beta and gamma types, and the quality factor of is and and it has the quality factor of 1.0, what will be his daily dose equivalent in megas? What's SV? You know what? It's SV's SV. We say SV. It's a milli SV, yeah. So that means we gotta find what SV is first. So then we use the so that's basically the SV equals AD times quality factor. So that means DE will just equal, because we found out what AD is, 2.88 times 10 to the power negative 2 times 1, which is just 2 times 88 times 10 to the power of 2 negative 2. But we want it in, this will be SV. We want it in milli SV. So we time it by 1,000. So we get 28.8 milli SV. Yeah. And the radiation, yeah, that's it for C and D. They want us to find if a dose of 5 sieverts, okay, it's not SV sieverts. What are these weird words? Sieverts is likely to be fatal in 50% of the population. What would you estimate the life expectancy of the patient to be? It says it's likely to be fatal for 50% of the population. So assume the guy is unlucky and he dies, and he is the 50% that dies. So 5 SV is basically 5,000 milli SV. So we just have to, because this is the daily intake, which is how many days he can live. So we do the 5,000 milli SV when he dies, divided by 28.8 milli SV, the both milli SV. So that's the daily input, and then we can use 5,000 divided by the answer. We get 173.61 days. So it's around 174 days. That's his life expectancy. That's pretty sad. He's gonna be dead like soon. Okay. Now we're gonna move on to the next topic, which is harder because physics. It's actually getting hard. Okay. It's the binding energy subtopic. Energy. And we'll do a question. It's quite long and I don't like it, but we have to do it anyways. Okay, let's see the question. Flip to the page. Here, okay. The question says, after absorbing a neutron, a uranium-235 nucleus can fission to produce barium-141 and krypton-92. And then for part A, we want to write the equation for this reaction. So A, yeah. So we just write Uranium 235. Uranium, pretty sure it's 92. Yeah, uranium is 92 plus nucleus, neutron. I mean, and it becomes what does it become? Barium 141. Okay, I was pretty close that time. We believe the iPad. Yeah, 56 plus krypton, and then let's check if it's balanced. Yeah, because I don't in physics like no neutrons or protons can be created or destroyed. So that's the mass. That's the mass. So we just do. So that's 23236, and this is 233. So it's missing 3 neutrons. So we just add them here. So they're not said in the question. It's probably because they don't care where the neutrons went. I think the small particles went after the reaction because fission they want energy. They don't want to know. They want to get stuff. They want to get neutrons. Neutrons are useless. Basically. And then that's part A. Let's write the equation. Calculate. Part B says calculate the energy that will release from the fission of a uranium 235 atom. So for that, we want to use the E equals mc squared formula. So it asks us to calculate the energy. So we want to find this. But C is just speed of light, so we know that. But we want to find the mass. The mass, so we use the starting mass plus this mass. So we should be given the masses for each thing, yeah? So let's list them here. So uranium 235 equals 235.1439 U's. Barium 141 is 140 times dot 9144 U. Krypton 92 is 91.9262 U, and a neutron is 1. Okay, 1.00867 U's. Let's find the change in mass in terms of U first. So that's basically just 235.0439 plus 1.00867. Let's move this down a bit. Oh my god. Minus 140.9144 minus 9262 minus 3 times 1.00867, and that will equal to, let's do that, 135.0439 plus 101.00867 minus 140.9144 minus 91.9262 minus 3 times 1.00867, and we got 0.18596 U, and we're going to convert it into kilograms because in the you get E equals mc squared, you have to use mass in kilograms, so we use the formula to convert it. So basically 1 U equals 1.6605 times 10 to the negative 27 kilograms. So that means it will equal to, so we just have to time this number by 1.6605 times 10 to the power of negative 27, and we get and we will get 3.087868 times 10 to the power of negative 28 kilograms, and now we can find the energy. So energy equals c squared, so that we can just use this number times times 3 times 10 to the power of 8 squared. We'll do that on a calculator. So times bracket 3 times 10 to the power of 8 squared, and we get 2.77907922 times 10 to the power of negative 11. 2.78 times 10 to the power of negative 11. And that is in joules because it's energy. That's it for this question. And now we move on to the next one, which is, I don't know why they put this last question as B, but it asks us to calculate the mass in kilograms of a single uranium atom. So that's just whatever listed here. So it's 235.0439 times this weird converting number, so 1.6605 times 10 to the power negative 27, because this is in U, this is in this, and this will convert into kilograms, so that basically is 235.0439 times 1.6605 times 10 to the power negative 27, and we will get 3.9029036 times 10 to the power negative 25, which equals 3.90 times 10 to the power negative 25, and this will be in kilograms. That's it for this question. I don't know why, it's kind of easy. It's kind of easy. And part D asks us that hence calculate the number of uranium-235 atoms in 1 kilogram pure uranium-235. So we know that one atom is this heavy. We want to know how heavy, how many particles is in 1 kilograms. So if each atom is weighs this much, then 1 kilogram of 1 kilogram divided by this much will get us how many atoms there are. So just 1 divided by the answer, 3.9 times 10 to the power negative 25. We use the actual value on the calculators. So 2.56219471 times 10 to the power 24. 24. Then that's pretty. Oh yeah, no, it's nanoparticles. Of course, it's big. 2.56 times 10 to the power 24. It would be atoms, or would it ask? Atoms. Okay, so now we will do part E. Part E says estimate the energy that will be released from the complete fission of 1 kilogram of uranium-235 atoms, and assume what would you have to make to calculate your answer? What assumption do you have to make this to calculate? Okay, so we know that every single atom of uranium-235 will generate this much energy, and we found out how many particles are. We just have to time these numbers. Oh my god, I just deleted it. So we just have to time this value. So around 2.56 times 10 to the power 24 times this value, which is 2.78 times 10 to the power negative 11. I don't suggest you do this in tests, because the teacher will be confused why you use the smaller numbers when actually using exact values in the calculator. So we'll actually put in 2.77907922 times 10 to the power negative 11, because when you want to use a more exact value, and this equals to 7.120542163 times 10 to the power 13, and that is around 7.12 times 10 to the power 13, and that would be in joules. That's a lot of energy for 1 kilogram of something. Like that's a lot of energy indeed. And what assumption I have to make up? I have to assume that I have to assume that all of the uranium, let's capitalize it, uranium 235 will undergo this exact fission reaction, as like some particle can get like hit by a neutron twice or like not get hit at all. So in real life, definitely will definitely not get that much energy because some will just not react and we'll just not get the energy back. And like maybe we'll get some weirder products because one got hit too much and stuff like that happens. Real life is not perfect. Okay, now we go to the next question. And it asks us, a nuclear power station produces 9.76 times 10 to the power 13 joules of electrical energy per day. Estimate the mass of uranium 235 required to produce this energy. So look, we have the energy it produces. We have the energy that it wants to produce. This is the energy it will produce with 1 kilogram. And we want to know how much do we need to get the higher amount of energy, because it says here 9.76, which is the both times 10 to the power 13, but 9.76 is bigger than 7.212. So we'll just use 1 kilogram of something times 9.76 over our 7.12 times 10 to the power 13. I will use the exact value, so it's literally just 9.76 divided by answer. So we get 1.37068214 times 10 to the power 13, negative 13. And that is around 1. Wait, that's not right. Oh, I forgot the times. Times 13. My bad. Yeah, my bad. Just have to times 10 to the power 13. And we will get this without that. So 37. So that's the kilograms that we need to produce a higher amount of electrical energy per day. Yeah, that's it for the two questions. They're way harder than the ones from yesterday, as these are more detailed topics and they require harder calculations and actual nuclear fission reactions and stuff. Fission reactions harder because it's like not even achieved. It is achieved, but like it's not practical yet in real life. So like no one cares, and it's hard. And I haven't even done the volts things. So like this topic's kind of hard. I might do more videos. Probably not. I'll probably move on to the next one and then I'll come back to it later because it's kind of hard. All right, bye bye.